Since we have limited time in class, I wanted to make sure that I took the time to make a video about how we actually get the integrated versions of the rate law. To derive the first order integrated rate law, we're going to start with our regular old first order rate law. That'll look like rate equals the rate constant times the concentration of thing A for the purposes of this video. We can also write the rate of the reactant that's decreasing as a negative change of the A concentration over change in time equals the rate constant times A. Now, if you've taken calculus class, you know that we need to do a technique called the separation of variables first. Before we can integrate this. That's because we have two different kinds of variables happening here. We have time and we have concentration. So we need to make sure that those two things are on different sides of our equation. So what I'm going to do is I'm going to divide my concentration over to the other side. And multiply my dt over to the right side. Now I'm ready to integrate. I'm going to integrate between time equals 0 and time equals t to keep it general. And I'm going to make sure that that looks the same for my concentrations by putting a little 0 at the bottom of my initial concentration and putting a little t at the bottom of my on the bottom of my concentration. So here we go. First of all, I'm going to have to look up what these integrals are because it's been a while since I did them. So the integral of 1 over the concentration of A, which I'll denote x for now, is going to be equal to the natural log of x. That's the hard one. The other one looks like it's just a constant in front of my dt. So how do I integrate constants? That's a good question. From what I recall, all you have to do is put down an x plus c. For us in chemistry land, that's going to make my situation look like integrating 1 over concentration of A dA between the first concentration, or the initial concentration rather, to the concentration at time t equal to negative k dt. Just a quick note, I switched where my negative sign was on my equation from the left side to the right side to make sure that my equation will end up looking pretty at the end by dividing by 1 on both sides. Now it's time to write out the answer to the integrals. We'll see that the integration of 1 over A is going to be the natural log of the A concentration. And then I like to write this as going between the A concentration at time t all the way down to our initial concentration equal to the negative kt, now that we have that time variable in there, going between time t and time 0. Okay, now let's write it out. This will look like the natural log of the concentration of A at time t minus the natural log of the concentration of A initially equal to the negative kt minus the negative k of 0. This last chunk at the end will end up being 0, so we won't have to worry about that portion of the equation. Now to make it pretty and to match the equation that's in our textbook, I'm going to add the natural log of the initial concentration to both sides. And we'll end up with a nice linear looking equation with the natural log of concentration of A at time t, being our y for y equals mx plus b, equals negative kt plus the natural log of the initial concentration. Again, it's really cool how this ends up looking like a linear equation. You can expect, if you have a first order reaction for the natural log of your concentrations, to have a plot that looks like this, with our y-axis being the natural log of the concentration and our x-axis being time or reaction progress. And that's how we derive the first order integrated rate law equation and what it looks like when it's plotted.